All right, folks, thanks for joining us. In the interest of time, we will get started. So, hello and welcome to the June 2025 RR-CLaN seminar. I'm Dr. Alan Stevens, the Director of Research at Northern New South Wales Local Health District. And today I'm thrilled to guide you through a session on an introduction to basic statistical analysis in Microsoft Excel. To officially get us started, we acknowledge the traditional custodians on the various lands and waters where we work and live and are joined from. Today, we acknowledge the traditional custodians of the culture, their connection to country, and their contribution to the livelihood of regions. We pay our respects to the ancestors and elders of the regions and to all Aboriginal people, past, present, future, and any Aboriginal people joining us today. So, welcome. For those of you that are unfamiliar with the Rural Research Collaborative Learning Network, and we are a large consolidated network spanning most of New South Wales, so operating the bulk of all the LHDs, the Health Education and Training Institute. We also incorporate a number of health services in Queensland as former members, but we're spread far and wide organically. We know that we're having attendance from other states and territories and registrations also for people internationally. We record all the sessions that we do through the network. We've got a YouTube channel where we post all of the recordings. So if you're interested in revisiting any of the content or you've missed some sessions, please access the link there to get to the YouTube channel. Just a little bit of housekeeping. So we're expecting a fairly large attendance today. We try and encourage people to keep their microphones muted if you can. We're also recording the session, as I just said. If you don't want to be in the recording, just simply turn off your cameras. We do encourage you to ask questions. So throughout the seminar, we'll attempt to open up for questions as we go, as we cover off some of the statistical techniques. Jen will help me facilitate that. Try to ask questions using the chat function so we can get to them. At the end of the session, if we do have time, we'll open the floor up and take some live questions there. Right. Yep. So just a little bit about me. I'm the Director of Research at Northern New South Wales. So in this role, I have overall responsibilities for research efforts and governance operations, research development support, and also strategic engagement with the broader ecosystem. I'm a mixed background scientist. I did my PhD in the molecular bioscience, but also formally trained as a biostatistician doing lots of biostats. My research interests are at the interface between the two. In terms of the presentation overview today, I'm going to be covering a number of different areas, one of which is comparing a mean to a reference standard. Comparing two study group means using a student's t-test, comparing three or more means. Yes.
Sorry to interrupt you. It's just Jen here. Just letting you know, some people are noticing audio dropping off. So if you could speak a bit louder, that would be wonderful.
Yeah, perfect. I'll keep my mic up. But thanks, Jen, for letting me know. Thanks for that. Hopefully this is clear enough. If there aren't any more issues, Jen, just try to rectify them. Thanks. The third statistical technique we'll be covering is comparing three or more means using analysis of variance. Probably familiar to most people in this heard of it. And then we're going to finish off with correlation analysis and regression analysis. It's simple regression. What I'm not covering today are measures of central tendency, such as the mean, median, and mode, measures of variability, such as the range, interquartile range, the variance, standard deviation, standard error, and like. Measures of frequency, so incidence, prevalence, and rates, and then measures of association, such as differences, or ratio scale measures, such as risk, odds, rate, or hazard ratios. So we're going to get straight into it. The first statistical technique we're going to cover is the one-sample t-test. Now, the premise of a one-sample t-test is to compare a mean to a reference or a standard. There are some assumptions, the first of which are data are sampled from a continuous variable, and they are normally distributed over the sample size. I'm going to go on a bit of a tangent now and talk about something called the central limit theorem. And if the sample size is small, we do want the data to be sampled from the distribution. But if it's of sufficient size, it doesn't actually need to be normally distributed. And we can rely on this theorem to do that. What this theorem is, and it's probably my favorite theorem, is it notes if X as a random variable has a distribution with mean mu and a standard deviation here, then for n that is sufficiently large, the sampling distribution of the mean is approximately. It can be further shown that the variable z, denoted by the difference between the sample mean and the population mean divided by the standard deviation over the square root of n, is approximately standard. So if you're not following all of this, don't worry too much about it. We're going to go through it in a bit more detail. Just the take-home message is focus on the sample size is sufficiently large. In terms of explaining what the central limit theorem is and how we can use it, so you can imagine we've got a population of all observations for a particular trait or variable. For this one, I'm going to use the household income or individual. Think about that as being something that's not normally distributed. It's probably highly skewed variable. Practicality, it's really difficult to obtain totality of the observations. So this is why we use sampling, for example, in statistics. We can repeatedly sample from that population. So if you do a thought experiment and you repeatedly sample many times, I'm talking hundreds and thousands of times, attempted to depict it here. There's only 30 of them, but ignore that. We're sampling many times. For each of those samples, we can calculate the mean, which is my X bar on the top, and then we can plot those means in a distribution. What the central limit theorem tells us is if the sample size in each of those samples, so it's an inherent property within a sample, increases, the distribution of these means will tend towards the moderate. And we can use this powerful fact in our advantage, meaning that we can actually analyze data from non-normally distributed populations using our parametric analysis. There is a term I reference saying sufficiently large. So what does sufficiently large mean? And it's largely undefined, probably does require some type of empirical analysis on a per distribution basis to establish it. What I've included here, though, is reference to an article which has kind of explored this and can give you an insight into what is sufficiently large. And I can tell you what, it doesn't need to be that large. In this particular study, the authors analysed the distribution of medical costs. You can see it's highly nominal, so it doesn't follow that normal curve, the bell-shaped curve we expect from distributed data. What they proceeded to do is randomly sample from this distribution many times. Each time they sampled from it, they had a sample size of 65, 129, 324, 487. I don't know why they chose those, slightly odd. And then they plotted the mean of these many samples per those two sizes. So if we focus on the first one here, you can immediately see already that even a sample size as small as 65, its sampling distribution of the mean does look like a bell-shaped curve. So what this is telling me is your sample size doesn't actually really need to be that large in order to use these parametric tests that we're covering today, even if they're drawn from non-normally distributed samples. So I didn't expect everyone to follow all of it. Hopefully you guys learned a little bit. The take-home message is focus on trying to get a sufficiently large sample size when you want to do any of these statistical tests that we're going to cover today. And something as small as 60 or 65 or whatever it was could be sufficiently large. So we'll go back now to our one-sentence test example. The example we're going to use here is based on a hypothetical data set, blood pressure and potential covariates and predictive factors. So this is a hypothetical data set. It's not real, it's simulated, but it's simulated in such a way that it's plausible. What we're going to do now is do one sample t-test to assess whether the mean blood pressure sample data is significantly different to a population mean or a reference data. In this case, it's at 120 millimeters. We're going to proceed to do demonstration in Excel. Before we do that, I have to make a note that in order to do the things that I'm going to show you, you've got to load the data analysis tool pack in Excel. For some reason, I don't know why, it doesn't come as standard. At least it didn't come as standard for me. Now, I've put in a link here, which I'll share the slides with everyone on how to load that data analysis tool. So what we're going to do is attempt a live demonstration. We go to our study data, which is here. And we want to look at our blood pressure data. So this is probably not the most informative. I haven't given these variables. What we're going to do is grab blood pressure data. We're going to copy, create a new spreadsheet, paste it. Now, some of you that have attempted to do this before probably know that Microsoft Excel actually doesn't cater in its list of different statistical tests for one simple t-test. But what we can do is a workaround that, in effect, tricks Microsoft Excel to do the mathematics of the one sample t-test. The key is in how we structure the data to do this. So remembering my example was trying to compare the mean data to a reference value of 100. I'm going to set up the data in a specific way to do this. So I've created a new variable or a new field, standard reference range, entered two values and two values only, and they're identical and they equate to the population reference standard. Next thing we do is we go to our data tab, navigate to the section here, which has the tools that we want data. Click on there. We have to find something called a t-test to sample assuming unequal variances. Remembering we're tricking Excel to do a one sample t-test for us. And the way we do it, we structure the data in this particular way. So what we're going to do is this still has the data from my previous examples. Clear that. Start from scratch. We'll select the variable one range, which is our study.
Didn't see the invite.
Study data. Yeah, just remind everyone to stay on mute if you can. So we'll select our study data and then we'll select the data for our standard. I select labels because when I selected the data for the various variables, there are labels in row 1. And then I'm going to select an output range and click OK. So this will do our one sample t-test. This is actually correct titles. You can put that one. And I'll just go through what the up means. So it's done some descriptive statistics for us. It's calculated the mean blood pressure in our study sample, which is 126. It's mercury. The reference data obviously is 120. It's calculated the variance, so 4 number of observations. But the key, I guess, to interpreting this is kind of like usual, and you might think back to your undergraduate statistic days, is you want to look at the statistic that comes with it, which for a t-test is a t-statistic, and then the associated p-value. And remembering that the way you interpret the p-values is comparing it to a pre-specified threshold. It's usually called an alpha level, and it's usually set at 0.5. And the general rule is if your p-value is smaller than your threshold, it indicates a significant test. And if it's larger, it's not. So in this case, we've got a very small t statistic, a very large p-value. It's certainly a lot bigger than 0.5. And it tells us that the study sample mean blood pressure of 120.6 is not significantly different to the standard reference we denoted as 120. And that probably makes sense to most people. So we'll go back to our PowerPoint slides, and that is how you trick Microsoft Excel into a sample t-test. So Jen, I'm just going to go to you. Have there been any questions in the chat? Anything come up?
No questions about what you're doing, Alex.
Okay, perfect. So hopefully you guys can hear me okay. I think Jen now's got her hand up. Jen, if you've got a question, Lee, if you've got a question.
Alex. Just a quick question. How does this relate to the potential covariance and predictive factors?
It doesn't. So my reference to covariance and predictive factors was the data I simulated, because the data I simulated has blood pressure. It's got other things in there like body mass index, diabetes, and socioeconomic status. What I'm showing today are very simple tests. They're all univariate tests, and it's impossible to adjust in a way for the covariance and predictive factors. So I believe that answers your question.
Thank you.
No worries. If there are no other questions, we're going to move on to the next statistical test, which is a two-sample t-test. The purpose of a two-sample t-test is to compare the means of two samples. In this particular example, we're going to test the significance of the difference in mean blood pressure between those with and without diabetes. Do another demonstration in Excel, but before we get to the point, it's important to highlight that Excel doesn't calculate the estimated mean difference. We can do that ourselves if we want. And it doesn't calculate the 95% confidence interval of the estimated mean difference. And why I've included that is it's usually out of everything that statistical tests do, a confidence interval is kind of like the most useful thing. But Microsoft Excel is good, but it's not specifically designed in a way to run statistical analyses, and some bits and pieces are missing. What we're going to do is go to our data. Still interested in blood pressure. This time we want to look at how that might differ by diabetes status. Let's select a bit more data this time. Go to our Microsoft Excel sheet and we'll enter create a new spreadsheet. What we're interested in seeing is whether there's a significant difference in blood pressure between those with and without diabetes. So I'm just going to clean this up a little bit and just keep the variables that are interesting for us, what we're interested in. So we want to keep diabetes status and blood pressure. First thing we're going to do in order to structure or set up the data correctly is sort by diabetes status. So this has nicely sorted my data to those with, without diabetes, and diabetes. Next thing I'm going to do is create two new variables for the data by group. So we're going to select all of the data for our non-diabetics. Paste it there. We're going to do the same thing for our diabetics. And paste it there. So this will be a bit of a recurring theme on how you set up the data for at least a two-sample t-test and some analysis of variance. What we'll do now is we'll go to our data analysis tab and we'll look for a two-sample t-test assuming equal variances. We're going to clear all of this or start from scratch. Select the data for our non-diabetes group. Same thing for our diabetes group. Got labels in the first row and we'll select another. Okay. So it comes up with a chunk of output. It does calculate some descriptive things, such as the mean blood pressure in each of our study groups, the variances, which may or may not be similar, an estimate of the forward variance, but we go to what we're really interested in, which is the t statistic. It's a decent size in terms of an absolute value, so -4, and the p-value is also very, very small. So it's 9.5, 10 to the -5. So we can actually have a look at what that really looks like in the notation, which is better. It looks something like that. So if we go back to the same principles as before, we want to compare this p-value to our threshold of 0.005, 0.05, sorry. And if the p-value is smaller than that threshold, it indicates there's a significant test result. What this would say for us is that the blood pressure of those in the non-diabetic group is significantly less than that of blood pressure in diabetes group. We could calculate, if we wanted to, the difference between groups. So it's roughly 15, and it tells us basically that that difference of 15 is a significant difference in this statistical sense. Back to my slides. This is what the output looks like. Just to finish up on the two sample t-tests, there are some assumptions associated with it. First one there is the samples are independent. What does this mean? It basically means that the selection of observation from one sample does not influence the selection of observations from the other. The populations from which the two samples were derived follow normal distributions. Just bear in mind, though, we covered, or attempted to cover, the central limit theorem, and this applies to this test as well. So if the sample size n is sufficiently large, you don't actually need to sample from a normal distribution. And then ideally, the populations should have equal variances. This is known as homogeneity variances. In the case that it's not, what you could do is go back to your Excel spreadsheet, and you could rerun this analysis using the t-tests using or assuming unequal variances. So we set up the data very similar ways. Select the data from our diabetes group, non-diabetes group, got labels, have a slightly different output. This is what it comes up with. So one thing you might notice, it doesn't have a full variance estimate because it assumes unequal variance. The mathematics that underpin the unequal variances approach to the two sample t-tests essentially results in an adjustment to the degrees of freedom. It does also result in a slightly different way that you calculate the t-statistic. It's quite slightly different. Invariably, in this hypothetical example, it's the same result. There is a significant difference between the two groupings. Go back to the slides. So pause here for any questions. Anything come through, Jen?
Nothing that hasn't been answered. Dan's answered a couple of questions that were related to the one sample t-test, but nothing else has come through.
Awesome. Thank you. So people following, we'll just move on. So we
have another question that's come up, Alex.
Yeah,
from
sure.
Clarissa, which is, why did the equal variance test result in unequal variance?
Why? Do you mean this? Not sure I'm following the question.
Yes.
Whoever, yeah. So there are ways to establish whether the variances are different or not. And you could proceed to do that test to indicate which approach you would use. But I didn't have time to go into it today. You could, I guess, one approach is to do both, a t-test assuming equal variances and a t-test assuming unequal variances, and see how different they are. The t-test using or assuming unequal variances will invariably probably approximate the t-test assuming equal variances if the variance is 3. So you could probably go with that approach to cover off on all bases, actually, if you really want to. Hopefully that answered your question. I'm not sure it did.
We've got another question in the chat, which is, are you going to test the assumptions normality before running the test? If yes, how can we do that in Excel?
I'm not sure how you do it in Excel, and my intention was not really to cover it, but it's a really good question. I did note here in the assumptions that you can assess normality using histograms. So you could plot them if you wanted to. There's things called PP plots, which are probability plots, or QQ plots, which are quantile plots. And they are a mechanism to assess deviations from normality. I think what I'd be favoring, though, there is they would really only apply if the sample size is smallish. If you feel like you're approaching a sample size which is sufficiently large, which I was trying to communicate with my central limit theorem tangent, then you kind of don't need to do that, if that makes sense. Anything else in the chat?
We do have more coming through.
Right.
Which is, so the next question that's come through is, how do you choose whether to go for unequal variance or equal variance tests?
Yeah, good point. I think this was related to what I was saying previously. It's if the variances are wildly different, you would probably go with a test using unequal variances. For this hypothetical example, my eyeballing of the variances suggests to me that they probably are different. And for safety, I would probably proceed to do a test using unequal variances. There are ways, statistical methods, that would enable you to do a test of whether these variances are significantly different or not. I'm not covering them today, just for simplicity, but you could choose to do them. So they're called tests of homogeneity variances. A popular one is Levine's test. It's often included in other dedicated statistical platforms like SPSS. It's common to do that. Whether Excel can do it, I'm not quite sure. Next question, Jen.
All done. Thank you.
Done. Excellent. Thank you very much for the questions. So what we're going to cover off now is the third statistical technique, which is comparing 3 or more means using analysis of variance. The ANOVA itself is an omnibus test or a screening test, in that it actually won't tell you where the differences lie, even if you get a significant result. In this example, we're going to test the significance of the differences in means between 3 socioeconomic status group, and that is mean blood pressure we're going to compare. So we'll proceed to do our demonstration. Excel, we're going to select our data. We're interested in socioeconomic status and blood pressure, so we'll select that. Copy. Go to our Excel spreadsheet. Choose a new sheet. Place. We're going to sort and order the data like we did before, and then create new variables for each of our socioeconomic status groups. So we'll select the blood pressure for the advantaged group, blood pressure for the average, and then the disadvantaged. Same thing as before, we go back to data analysis, except this time we're going to look for ANOVA single factor. Slightly different here in that the input range has just given us one option. We want to grab all of the data grouped by columns. So that's okay. We've got labels in the first row, and then we're going to select the output to be here. The output provides us a number of tables, in fact, 2 tables. One is a summary table, which provides some summary statistics of the blood pressure in the groups. I think probably the most interesting is the average blood pressure in each group. So 115 in the advantage, then roughly 124, 125 in the average and disadvantage groups. It also spits out the analysis of variance table. I think the key things again to look at there is the statistic that comes out, which is the F score, and then the p-value associated with that statistic. I would focus on the p-value. Same thing as before, we're going to compare it to our alpha value of 0.5, and if it's smaller, it's indicating a significant test result. So in this case, 0.02 is smaller than 0.05, and it's telling us that there is significant difference in the mean blood pressure between at least 2 of those groups. What it doesn't tell us is which groups are significantly different. We can probably deduce, based on what we're seeing here, that the advantaged group has significantly lower blood pressure than average and disadvantaged groups, but we would need to definitively prove this by doing pairwise t-tests between the groups. So we would in fact have to do 3 pairwise t-tests, and you could use the 2-sample t-test I showed you before. Go back to our slides. That's the output there. I won't go through all of the assumptions and what to do when the assumptions are violated. I'll leave this with you guys as a bit of homework. Just suffice to say that many of the principles and concepts that we've already covered are also relevant for ANOVA. Yeah, now I might open it up for questions now and see if anything's come through.
Nothing yet, but we'll give it another minute.
Okay, so in the interest of time, I just might get through, or might proceed. If anything does come through, we can tackle them at some point or towards the end. The last 2 statistical methods we're going to cover are kind of related. One's correlation analysis and one is regression analysis. There is an overlap in, the testing and the mathematics, but it's slightly different, I guess, in terms of the intent. We're going to start with correlation analysis, and the intention of correlation analysis is to assess the relationship between 2 variables. The example we're going to go through here is assess the strength of the relationship between blood pressure and body mass index by calculating something called the Pearson correlation coefficient. Yes, Jen.
So sorry to interrupt you. So we've got a few questions have come through now. So we've got a question is, what is variance? The next question is, how does a log transformation improve normality? And we've got a question about, is it intragroup variance or something else?
Yes, all very good. So I'll tackle the variance one first. And the variance is kind of exactly that. It can be intra-group, so within a group. And the variance is essentially a measure of how the observations within a study group vary around the mean. So if it's tightly clustered around the mean of that group, the variance will be small. If it's widespread around the mean of that group, you get a large variance, right? Analysis of variance works in a particular way that it does a comparison essentially of the within group variance to the between group variance. And it's the ratio of those variances, which are actually both estimates of a particular variance, gives you the significance. So you can imagine we've got 3 groups. Blood pressure, we can calculate the variance within each group, then we can calculate based on the totality of observations the variances between the groups, and it's that ratio, so to speak, of the within and between variance that is the basis of analysis of variance. Sorry, Jen, the middle question was, the log transformation. Yeah, so the log transformation has a natural interpretation in statistics, in that it is still a little bit more difficult, but somewhat intuitive to interpret data or analyses arising from log transform data. You can use other transformations, but then it becomes much more difficult to interpret what the analyses mean. So that's why I made reference to a log transformation and only that. I don't have time to go into the exact details today of how you would interpret it, but my recommendation is, if you're going to try any transformation, try the one transformation, which is a log. Otherwise, don't bother doing it. Maybe use a non-parametric test or something else. So it probably is a discussion point that's beyond what I wanted to cover in this session, but it's a good question. Yeah.
And Alex, we've had one more question come in, which is, why do an ANOVA and not just jump straight to the 3 t-test?
To avoid you doing tests. So the purpose of the ANOVA is a screening test, and the single screening test will tell you whether it's worth pursuing individual pairwise t-tests. And the whole point is to avoid you doing too many tests. Because if you do, an exorbitant number of tests, eventually by chance you'll come across a test result which indicates significance, but it's actually an error, right? It's just by chance that the data has come up in such a way that you get a significant test result. So that's the beauty of the analysis of variance being a screening test. It allows you to determine whether you want to go on and do those pairwise comparisons. Good question. So we'll go back to the correlation analysis. The example we're going to cover in this demonstration is to assess the strength of the relationship between blood pressure and body mass index. I'm going to do that now. Go to our study data. Again, we're interested in blood pressure and BMI. I'm going to grab all the data. It's going to be useful for what we do in the regression. Going to get rid of everything we don't want. What we want is to explore the relationship essentially between these two variables, BMI and blood pressure. Go back to data analysis, go through the correlation. Okay, happy with everything. Start from scratch. I'm going to select the data we want. It's grouped by columns. Then we're going to select an output range here. And this is what it gives us. So the problem with correlation in Excel is it actually doesn't give us much. It gives us a correlation matrix, which gives us an idea of the relationship or the relatedness between variables. So obviously BMI is perfectly correlated to itself, and it has a correlation of roughly 0.6 with blood pressure. What does this mean? To me, 0.6 represents a modest level of correlation. It's fairly correlated, so to speak, but we can't make any inferences about it. So we have to do a few manual calculations to make up for the deficiency. What we've got to do is calculate the standard error associated with our correlation coefficient, a t-score, and then the p-value associated. So what we'll do is proceed to do that now. First things, we're just going to put a few things. So n was 100 pairs, the degrees of freedom was 2. We're going to calculate the standard error of the correlation coefficient. which was given by the square root one minus correlation coefficient squared divided by n. So this gives us the standard error, which is the measure of precision in our estimated correlation coefficient. We need to calculate t-score associated with that, which is given by correlation coefficient divided by the standard error. And then we want to calculate the p-value. So, I know I moved really quickly in this. This is why we record it. We always go back to the recording to see the steps it took. But what it suggests is p-value associated with this correlation coefficient is highly significant. So from an inference perspective, it's telling us that we simply haven't got that relationship by chance, and the chances of getting data in such a way, assuming they were completely unrelated, is very, very small. So then we could say, look, we've got a correlation coefficient of 0.6, and it's statistically significant. Let's go back to the slides. What it looks like. These are the assumptions of correlation analysis, very similar to before. The samples are independent. Each variable is drawn from a normally distributed population if n is small. The inference, we did it in a particular way. We assessed hypotheses about the correlation coefficient using something called an uncorrelated bivariate normal distribution using the student's t-distribution. So that probably doesn't mean anything to anyone. Suffice to say that there are multiple ways to assess or to the inference of a correlation coefficient. So just before jumping onto the last statistical test, regression, Jen, has anything come through in the chat?
Nothing's come through on the chat at this stage. Thank you, Alex.
Thanks, Jen. Just again, stop me if something does come through and we'll answer those questions. Otherwise, proceed now to regression analysis. It's kind of related to regression, to correlation, that we are examining the relationship between variables, although it's from a slightly different perspective. So in this case, we want to examine the relationship between an outcome or a dependent variable and one predictor or an independent variable. Probably failed to mention here, at least I've written it down, we're doing simple linear regression, hence why we're only looking at one predictor. We are again going to have a look at our body mass index, systolic blood pressure, but we're going to look at it in this particular way. Is body mass index predictive of systolic blood pressure? Before we go to the demonstration in Excel, just to note, regression analysis does not establish a causal relationship between variables. So let's proceed to our demonstration. Go straight to our data. Data's already there. We've copied and pasted it for the correlation analysis. We can use the same data for our regression analysis. So go to our data analysis. We look for regression analysis. There. Start from scratch again. So we'll highlight the Y data, which is the dependent data, or the thing that we're trying to predict. This time, blood pressure. Then we're going to select the independent variable, or the predictor variable, which is body mass index. And then the output range, we're just going to select somewhere here and go OK. So the regression analysis is kind of getting a little more sophisticated. It does have numerous tables in the output. We can be assured, based on, I guess, the relationship or the similarity between correlation and regression, that some things look the same. We've got the same correlation coefficient. We get something called an R squared, which is literally this value R squared. Some of you may recall from introductory statistics that the R squared represents the proportion of the variance in the dependent variable, which is explained by the independent variable. So it's a common way to look at it. Regression does spit out an analysis of variance table. It's slightly different to, well, sorry, it's not slightly different. It's a very similar vein to an analysis of variance table. You interpret the F and the significance, which is the p-value. Happens to be exactly the same as the p-value derived when doing the inference or our correlation coefficient. That's reassuring. The last thing it spits out is this table here, which are the parameters of the regression equation. So the statistical model that describes the relationship between BMI and blood pressure is here. It gives us an intercept of 65, which I'll talk a little bit about in a second. Doesn't really need much data structure in this way. And then the gradient, so to speak, of the effect of BMI. What this basically means here is this 2.19 is that for every 1 unit in BMI, blood pressure increases by 2. Backtrack a little bit to the intercept. We analyzed the data in such a way that we didn't make any adjustments for the predictor, and we analyzed it for what this intercept is telling us is what is the blood pressure at a BMI of 0. So you can naturally understand that a BMI of 0 doesn't mean anything. So one trick that's commonly used by analysts and statisticians is that you will transform the independent variable to be a mean-centered variable. So basically, for the raw data, each of those raw individual points should subtract the mean. This is what this BMI-C variable means. And if we redid the analysis using BMI-C, we would have a far more natural interpretation of the intercept. And the intercept would effectively give us what the blood pressure is at the mean sample BMI, if that makes sense. So we've probably got a little bit of time. We can do this very, very quickly. We'll redo the regression, this time using the centered BMI variable. So the input range, the dependent variable stays the same. What we are going to change, though, is the predictor variable to be centered BMI. The output update here. Okay. This one actually changed the statistical outputs or the statistical testing. Everything will be the same. The R, the R squared, the ANOVA table. The only thing that changes is the natural interpretation of the regression parameters. So this basically is what the expected blood pressure at the mean BMI, if that makes sense. Just go back to the slides. That was regression analysis. These are some of the assumptions. So the assumptions, they're all important across all statistical tests, but they are vitally important actually in regression analysis. I've listed 3 here, that the errors or residuals are normally distributed. I'll speak to that very, very shortly. The relationship between the dependent and independent variable is linear. So we did a simple linear regression. You can do the analysis assuming that the relationship isn't linear, but you've got to specify in that way. It's a more complicated analysis. The last assumption here is constant variance of errors across the domain. Scarcity. The last thing is be careful of influential data points, particular data points that sit on the other end of the scatter. So this is a scatter plot of the relationship between systolic blood pressure and body mass index. What I mean by this first assumption here is that if you take each of these data points and draw a line to the regression the line of best fit and measured it and then plotted those measures in a graph, you want them to be normally distributed. The other one, which is the homogeneity of variances across the domain, is we want the scatter plots to kind of the points to be sort of evenly distributed across the entire length of the predicted variable. So we won't want them to be very close. We want the stop points to be very close, for example, on the lower end of the scale and then spread apart on the other end, because the regression interpretation and inference work. So that is it. Thank you for hanging on. I know we covered a lot of ground. We'll open up for questions. I think before we get there, I'll introduce the next seminar. So in a month, we've got Sean Grady, Senior Health Mathematician, the Data Sciences Platform at Hunter Medical Research Institute, will present on Survey Smarts, finding the best fit for health data collection. We'll distribute the slides from today's presentation. You can register using here. I'll add to the chat now our link to the evaluation survey. If you can let us know how we're doing, that's fairly important. That what to do. So Jen, if there are any questions, I'll open up the floor for any questions. Happy to take up any hands and certainly happy to answer any questions which have come in through the chat.
Thank you, Alex. Nothing in the chat at this stage.
Excellent.
A lot of thanks for you, Alex. People are asking where they can get the recording of the video.
Yeah, look, absolutely. So once everything's sort of done and dusted today, we'll download the recording, we'll upload it to YouTube, we'll distribute a copy of the slides, and I'll also include a copy of the data that we use. So if anyone's really keen, they can try to replicate some of the things we covered today. Yeah. So there is one question from me. How do we access the analysis tool pack in Excel? Yeah, so I think it was early on in the presentation. I do have a link to a resource online that demonstrates how you upload or you add the analysis tool pack. It's all fairly simple to do. It's another question, I think. Anna, pre-post intervention test for analysis of group meetings. Which of these tests would be the most appropriate pre-post intervention test for analysis? Sounds possibly like you would do a t-test if there's two groups, if there's more than two groups, potentially an analysis of variance. Bearing in mind, these are all entry-level statistical methods. We call them univariate analyses. They're not very sophisticated in terms of it doesn't systematically address things like confounding or covariance. So just an important thing to take home. Can't see any hands up. Can't see any other questions. That might be it. Lucille, are you able to suggest any research articles, book, or application to read related to your interest in presentation, please? Lucille, nothing on the top of my mind, but I'll take that on notice and see if anything comes up, and might include it in the correspondence. Another question from Rachel: does Excel do non-parametric analysis as well? Good question. I think it does. So I suspect if we go to our data analysis, I'm assuming some of these possibly, actually it doesn't look like it. Good question. Maybe not. Yeah. Sorry, maybe not. Okay. Excellent. All right, so I'm just conscious of time, so I might just draw this session to a conclusion. Thank you everyone for joining us. Hopefully we'll see you next month for Sean's presentation. So thanks again and enjoy the rest of your day. Thanks everyone. Bye.